Good morning, folks. Today I want to go over. I'm skipping over 9.9. It's something that we does need to get discussed, but I'm not going to go ahead and discuss it until uh, May, until after the AP test and reviews are done, because it's not necessary for the AP test, but I do want to go over it because if you do get the credits for Cal 1 and 2, it is something that it is discussed and you're expected to know. So just know that after our I guess AP test time, we will be going over content that is in Cal 2 but not taught on the test, because at the end of the day I need to teach the content, make sure that it is equitable, and that if you move on to Cal 3, you're not going to be lost or confused or knowing that I didn't teach you something, because I want to make sure we cover those gaps. So today I'm going to go over Taylor and Maclaurin series. Now, what's unique about the Taylor and Maclaurin series is that if they're in the proper form, they're always going to converge for all values of x within reason. So we've already alluded to the Taylor and Maclaurin's polynomials, and then if we were to continue, as opposed to stopping at the fifth degree or the fourth degree polynomial, and keep on going on for the nth term and beyond, we're gonna find that we have the Taylor and Maclaurin series itself. So to reiterate that, I'm going to go ahead and, this is from our textbook. If you look at page 669, you're going to know that right here, this is our Taylor and Maclaurin polynomial. It's Taylor when we don't know what C is, and then it becomes Maclaurin when C is 0. And we demonstrated that the more iterations that we do of the Maclaurin, the more it's going to match exactly what the graph itself looks like as well. Okay, so what I really want y'all to do today is not so much work out the problems per se. What I want you to do is I want you to find the Taylor series. I want you to find the Maclaurin series, as the case may be, for several of the problems today. And my idea is to do 3 or 4 terms and then try to find a pattern, because there's going to be a pattern for every single one of them. But for example, let's look at number 5 on the homework I'm going to give you today, which is on page 677. It says, in exercise 5 through 16, use a definition of a Taylor series to find the Taylor series and center at C for the function. So if f of x equals e to the 2x, so our goal is to find a series for this. So what we can do is let's go ahead and define it as, remember, Taylor is let's see here, where are we centered at? The problem we're centered at 0, so it's Maclaurin. So f of 0 plus f prime of 0x plus f double prime 0x squared over 2 factorial plus f triple prime of 0 over 3 factorial times x cubed, and so on and so forth. So we know that what I would do here, so f of 0 is 1. We can figure that out pretty quickly. F prime of 0. Well, F prime is 2e to the 2x, so it should be next there. Which means F prime of 0 is 2. And then F double prime of x is 4e to 2x, which means F of 0, F double prime of 0 is 4. And then let's see, let's do another one to see. I think I see a pattern already, but I want to be sure before I say it. So F triple prime would be 8e to 2x. Okay, so what's happening here is we go 1, 2, 4, 8. It's doubling every time. So that means it's going to be 2 F prime 0 x plus F double prime. So it's going to be, we have that here, 4 x squared over 2 factorial plus 8 x cubed over 3 factorial. Now, one thing you're going to notice I'm not reducing these, because technically this 2 factorial and this 4 can reduce to 2, but that's not going to reveal a pattern for me. So what my pattern is, it's going to be, let's see here, n factorial in the denominator. We know this number is 2n minus 1 because it's being doubled every single time my first term is 0. Oh, I guess I could just use n, because if we start at 0, so it'll be n, 2 to the power of n, and then x to the power of n. So I could even say this if I wanted to. And then the pattern is going to continue on, plus dot dot dot. So now if I were asked for in the summation form, e to the 2x is equal to 2x to the n over n factorial. Which is interesting because if we just had e to the x, looking at page 674 of the textbook, we clearly see that we know that e to the x, and I've also done it in the previous homework, in previous notes. Sorry. You can see the difference. This is the parent function. This is what happened. We added a 2 here, and notice the difference between this series and this series. Well, the answer is that there isn't much of a difference besides that this 2x here becomes a 2 here. So maybe you could use that pattern. So on this, I'm not going to give you actually a lot of instruction on it because I really want you to try to find the patterns yourself and make connections. So I want you to do one of the problems and then immediately come back and reference 674, page 674, that table that's there for you, and figure out what's going on there. Now, there are just one thing you really do need to know that could come up is that you really need to know several of the Taylor series expansions. So the first ones you need to know sine, cosine, e to the x, and 1 over 1 plus x. You need to be familiar with those, how to derive those. Actually, those are also on a homework, so you've already done them. But please make sure you know how to expand these using Taylor or Maclaurin series, using your power series. So your homework, all I'm going to really do is, like I said, emphasize again that you can expand these series. So your homework's on page 677. We've already done number 5. So 27 through 35 as well. If you have any questions, I'm in my office hours, and contact me via email if those office hours don't suit you.